Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. Wind, in its most elementary and perhaps most unremarkable definition, is simply the movement of air from one region of the atmosphere to another, and this movement is driven, as it has always been driven, by differences in atmospheric pressure that arise from the uneven heating of the Earth's surface by solar radiation. The Sun, which is located approximately 149.6 million kilometers from the Earth, delivers energy at a rate of roughly 1,361 watts per square meter at the top of the atmosphere, a quantity known as the solar constant, although it is not, in the strictest sense, entirely constant, varying by approximately 0.1% over the course of the 11-year solar cycle. This energy, upon reaching the surface and the lower atmosphere, is absorbed in highly unequal proportions depending upon latitude, surface albedo, cloud cover, and a great many other factors that are, individually, rather tedious to enumerate but collectively result in the fundamental temperature gradients that give rise to pressure differences and, consequently, to the phenomenon of wind. The atmosphere, which is composed of approximately 78.09% nitrogen, 20.95% oxygen, 0.93% argon, and trace quantities of carbon dioxide, neon, helium, methane, and various other gases, behaves in accordance with the ideal gas law to a reasonable first approximation, such that regions of higher temperature tend to be associated with lower surface pressure, while regions of lower temperature tend to be associated with higher surface pressure. This relationship, however, is complicated by a number of factors including moisture content, altitude, and the vertical structure of the atmosphere. And it would be an oversimplification to suggest that warm air always rises and cold air always sinks in a perfectly orderly fashion. Nevertheless, the basic principle holds that horizontal pressure gradients are established across the surface of the Earth, and it is these gradients that constitute the primary driving force behind all atmospheric motion, from the gentlest of breezes to the most destructive of hurricanes. The pressure gradient force, which is the force that acts upon a parcel of air in the direction from higher pressure to lower pressure, is expressed mathematically as the negative gradient of pressure divided by the density of air. In component form, this may be written as the partial derivative of pressure with respect to distance in the x direction, divided by the air density, and similarly for the y and z directions. The magnitude of this force is directly proportional to the steepness of the pressure gradient, which is to say that when isobars on a weather map are closely spaced together, the pressure gradient force is large and the resulting winds tend to be strong. Whereas when the isobars are widely spaced, the pressure gradient force is small and the winds tend to be light. A typical sea level pressure gradient in the mid-latitudes might be on the order of 1 to 2 hectopascals per 100 kilometers, which would correspond to winds of moderate strength, while in the vicinity of an intense extratropical cyclone, the pressure gradient might reach 5 or even 10 hectopascals per 100 kilometers, producing gale force or storm force winds. It was observed quite early in the history of meteorology, and indeed well before meteorology existed as a formal scientific discipline, that winds do not blow directly from areas of high pressure to areas of low pressure in a straight line, but rather follow curved paths that are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is attributable to the Coriolis effect, which is not a true force in the Newtonian sense, but rather an apparent force that arises from the rotation of the Earth about its axis. The Earth completes one full rotation every 23 hours, 56 minutes, and 4.09 seconds, which is the sidereal day. And this rotation imparts an angular velocity of approximately 7.29 times 10 to the negative fifth radians per second to all objects and fluid parcels on or near the surface. The magnitude of the Coriolis acceleration experienced by a moving air parcel is given by twice the angular velocity of the Earth multiplied by the speed of the air parcel multiplied by the sine of the latitude. At the equator, where the latitude is 0 degrees, the sine of the latitude is 0, and consequently the Coriolis effect vanishes entirely. Which is why equatorial regions tend to experience winds that blow more directly from high pressure to low pressure. At the poles, where the latitude is 90 degrees, the sine of the latitude is 1, and the Coriolis effect is at its maximum. At intermediate latitudes, such as 45 degrees north, where a great many of the world's population centers and weather observation stations happen to be located, the Coriolis parameter, often denoted by the letter F, has a value of approximately 1.03 times 10 to the negative fourth per second. When the pressure gradient force and the Coriolis force are in exact balance, which is to say when they are equal in magnitude but opposite in direction, the resulting wind blows parallel to the isobars rather than across them. This idealized wind is known as the geostrophic wind, from the Greek words for earth and turning, and it serves as a useful first approximation to the actual winds observed in the free atmosphere above the planetary boundary layer, which extends from the surface to a height of approximately 1 to 2 kilometers, depending on conditions. The geostrophic wind speed is given by the pressure gradient divided by the product of the air density and the Coriolis parameter, and for a given pressure gradient, the geostrophic wind speed is lower at higher latitudes, where the Coriolis parameter is larger, and higher at lower latitudes, where the Coriolis parameter is smaller. In practice, of course, the winds observed at the surface of the Earth are not purely geostrophic, because the frictional drag exerted by the surface slows the wind and causes it to cross the isobars at an angle, typically between 10 and 45 degrees, depending on the roughness of the terrain. Over smooth water surfaces, the angle of crossing is generally smaller, on the order of 10 to 15 degrees, while over rough terrain with buildings, trees, and topographic features, the angle may be as large as 30 to 45 degrees. This frictional modification of the wind is confined to the planetary boundary layer, and above this layer, in the free atmosphere, the winds are much more nearly geostrophic in character, particularly in the mid-latitudes where the Coriolis effect is sufficiently strong. The observation and measurement of wind has a history that extends back thousands of years, although the earliest records are naturally qualitative rather than quantitative in nature. The ancient Greeks, who were keenly interested in meteorological phenomena as part of their broader philosophical investigations into the workings of the natural world, recognized at least 8 distinct wind directions, which were represented by the octagonal Tower of the Winds constructed in Athens around 50 years before the Common Era by Andronicus of Cyrrhus. This remarkable structure, which still stands today, is approximately 12 meters tall and 8 meters in diameter, and each of its 8 faces bears a carved relief representing one of the 8 wind deities of Greek mythology: Boreas, the north wind; Kaikias, the northeast wind; Eurus, the east wind; Apeliotes, the southeast wind; Notus, the south wind; Lips, the southwest wind; Zephyrus, the west wind; and Skiron, the northwest wind. The wind vane, which is among the simplest and oldest of all meteorological instruments, has been used for determining wind direction since at least the 1st century of the Common Era, and quite possibly much earlier. The basic principle of the wind vane is exceedingly straightforward. A flat surface mounted on a vertical pivot is acted upon by the wind in such a way that the surface aligns itself with the direction from which the wind is blowing. The wind vane mounted atop a church steeple, barn, or other elevated structure became a common sight across Europe during the medieval period, and by the 14th and 15th centuries, wind observations based on vane readings were being recorded with some regularity at various locations. However, these observations pertained only to wind direction and provided no information whatsoever about wind speed or force. The quantitative measurement of wind speed required the development of specialized instruments, the most important of which is the anemometer. The word anemometer derives from the Greek word anemos, meaning wind, and metron, meaning measure, and various forms of anemometer have been devised over the centuries. One of the earliest known anemometer designs was described by Leon Battista Alberti, the Italian Renaissance polymath, around the year 1450. Alberti's device consisted of a flat plate suspended from a horizontal axis, and the angle at which the plate was deflected by the wind was taken as an indication of the wind's force. This type of instrument, known as a plate anemometer or deflection anemometer, was subsequently refined by various investigators, including Robert Hooke, who constructed an improved version in 1664, and a number of other natural philosophers during the 17th and 18th centuries. The plate anemometer, while conceptually simple, suffered from a number of practical limitations, including the fact that the relationship between the deflection angle and the wind speed is not linear, and the instrument is sensitive to turbulent fluctuations in the wind. A fundamentally different approach to wind speed measurement was embodied in the rotation anemometer, which operates on the principle that a set of cups or vanes mounted on a vertical or horizontal shaft will be caused to rotate by the wind at a rate that is proportional, or very nearly proportional to the wind speed. The most successful and enduring design of rotation anemometer is the cup anemometer, which was invented by John Thomas Romney Robinson, an astronomer at the Armagh Observatory in Ireland, in the year 1846. Robinson's cup anemometer consisted of 4 hemispherical cups mounted at the ends of 4 horizontal arms, which were attached to a vertical shaft that was free to rotate. The wind, acting upon the concave inner surfaces of the cups, exerted a greater force than upon the convex outer surfaces, thereby causing the assembly to rotate in a direction perpendicular to the wind. Robinson initially believed, and stated in his original publication, that the linear speed of the cup centers was exactly 1/3 of the wind speed, regardless of the size of the cups or the length of the arms, a proposition that came to be known as Robinson's factor of 3. However, subsequent investigations by other researchers, including Thomas Stevenson and William Henry Dines, demonstrated that this factor was not in fact constant, but depended upon the dimensions of the instrument and other factors, and that the actual ratio of cup speed to wind speed was somewhat variable. Despite this initial theoretical error, Robinson's cup anemometer proved to be an extremely practical and reliable instrument for measuring wind speed, and it was widely adopted by meteorological services around the world during the latter half of the 19th century. The design was eventually modified from 4 cups to 3 cups, a change that was found to improve the instrument's response characteristics. And the 3-cup anemometer remains to this day one of the most commonly used instruments for measuring surface wind speed at weather stations around the world. The World Meteorological Organization, in its Guide to Meteorological Instruments and Methods of Observation, specifies that the standard exposure height for surface wind measurements is 10 meters above ground level over open terrain, and that wind speed should be reported as a 10-minute average in most circumstances, although some national services, notably the United States, use a 2-minute averaging period. The development of the cup anemometer was accompanied by, and in some cases preceded by, various other approaches to wind measurement that are worthy of brief mention. The pressure tube anemometer, developed by William Henry Dines in 1892, operated on the principle that the dynamic pressure of the wind could be related to the wind speed through Bernoulli's equation. Dines' instrument consisted of a pressure head mounted on a wind vane, connected by tubing to a float manometer that recorded the pressure difference between the windward and leeward sides of the head. This instrument was widely used in the United Kingdom and elsewhere for many decades, and was particularly valued for its ability to provide continuous recordings of both wind speed and direction. Another important class of wind measuring instrument is the hot wire anemometer, which operates on the principle that the rate of heat loss from a heated wire is dependent upon the speed of the air flowing past it. When a thin wire is heated electrically and exposed to a flow of air, the convective cooling of the wire increases with increasing wind speed, and this cooling can be detected either as a change in the temperature of the wire, which affects its electrical resistance, or as a change in the electrical power required to maintain the wire at a constant temperature. Hot wire anemometers are capable of extremely fast response times, on the order of microseconds, and are therefore particularly useful for measuring turbulent fluctuations in the wind. But they're delicate instruments that are generally not suitable for routine outdoor use in the harsh conditions often encountered at weather stations. The history of wind observation is also intimately connected with the development of systematic weather observation networks, which began to emerge in the 17th century with the establishment of the first meteorological societies and academies. The Accademia del Cimento in Florence, founded in 1657, organized one of the earliest networks of standardized weather observations, which included observations of wind direction, although not wind speed. The Societas Meteorologica Palatina, based in Mannheim, Germany, established an even more extensive network beginning in 1780, with observation stations across Europe and even in North America. And the standardized instructions issued to observers included detailed guidance on wind observation. These early networks laid the groundwork for the modern system of weather observation that would develop during the 19th century, driven in large part by the needs of maritime navigation and the desire to improve weather forecasting. The transition from qualitative to quantitative wind observation was a gradual process that unfolded over several centuries, and it involved not only the invention of suitable measuring instruments, but also the development of standardized scales and classification systems that could provide a common language for describing wind conditions. This is a subject to which we shall return in considerable detail in due course, as it forms the central topic of this rather prolonged discussion. For the moment, however, it is sufficient to note that the challenge of wind measurement has always involved a tension between the desire for precise, quantitative data and the practical realities of observing a phenomenon that is inherently variable, turbulent, and difficult to characterize with a single number. Wind speed at any given location varies continuously in time, with fluctuations occurring on timescales ranging from fractions of a second, in the case of small-scale turbulent eddies, to hours or days. In the case of the passage of synoptic-scale weather systems, the instantaneous wind speed at a point may differ substantially from the average wind speed over a period of minutes or hours, and the peak gust speed during a given interval may be 2 or even 3 times the mean wind speed. This variability is quantified by the gust factor, which is defined as the ratio of the peak gust speed to the mean wind speed over a specified averaging period. And typical values of the gust factor range from about 1.3 over open water to 2.0 or more over rough, built-up terrain. The vertical profile of wind speed in the lower atmosphere is another important consideration in wind measurement and classification. Near the surface, wind speed increases with height due to the decreasing influence of frictional drag, and this increase follows a logarithmic profile under neutral stability conditions. The logarithmic wind profile is described by an equation that relates the wind speed at height z to the friction velocity, the von Karman constant, which has a value of approximately 0.4, and the roughness length, which is a parameter that characterizes the aerodynamic roughness of the surface. Typical values of the roughness length range from approximately 0.0002 meters over calm open water to 0.01 meters over short grass, 0.1 meters over low crops, 1.0 meters over suburban areas, and 2.0 meters or more over city centers with tall buildings. The concept of thermal wind, which describes the change in geostrophic wind with altitude, is another important element in understanding the vertical structure of the wind field. The thermal wind is not a wind in the conventional sense, but rather the vector difference between the geostrophic wind at two different pressure levels, and it is directed parallel to the mean isotherms of the intervening layer, with cold air to the left in the northern hemisphere. The thermal wind relationship, which is derived from the combination of the geostrophic wind equation and the hydrostatic equation, states that the rate of change of the geostrophic wind with respect to the natural logarithm of pressure is proportional to the horizontal temperature gradient divided by the Coriolis parameter. This relationship explains why the jet streams, which are narrow bands of very strong winds in the upper troposphere typically found at altitudes of 9 to 12 kilometers, are located above regions of strong horizontal temperature gradient, such as the polar front that separates cold polar air from warmer subtropical air. The jet stream wind speeds commonly reach 100 to 200 knots, and on occasion may exceed 250 knots, making them among the strongest sustained winds found anywhere in the atmosphere outside of tropical cyclones and tornadoes. The sea breeze and land breeze circulation is yet another example of thermally driven wind that has been observed and documented since antiquity. During the daytime, the land surface heats up more rapidly than the adjacent water surface, creating a local pressure gradient that drives a flow of cooler air from the sea toward the land, known as the sea breeze. This circulation typically develops in the late morning, reaches its maximum intensity in the early to mid-afternoon, and may penetrate inland for distances of 10 to 50 kilometers, depending on the temperature contrast and the synoptic scale wind pattern. At night, the circulation reverses as the land cools more rapidly than the water, producing a land breeze that blows from the land toward the sea. The sea breeze front, which is the leading edge of the advancing cooler maritime air, may be accompanied by a narrow band of cumulus clouds and, in some cases, enhanced shower activity. And it has been the subject of numerous meteorological studies dating back to the earliest days of observational meteorology. Mountain and valley winds, known collectively as slope winds or anabatic and katabatic winds, constitute another important class of thermally driven local wind systems. During the daytime, the air adjacent to sun-heated mountain slopes is warmed and rises along the slope, producing an upslope or anabatic wind. At night, the air near the slope cools by radiative heat loss and drains downhill under the influence of gravity, producing a downslope or katabatic wind. These circulations can be quite vigorous, with katabatic winds in particular reaching speeds of 10 to 20 meters per second in some locations, and in extreme cases, such as the Antarctic ice sheet, katabatic winds can exceed hurricane force, with sustained speeds of 50 meters per second or more being recorded at coastal stations such as Cape Denison in Adélie Land, which was famously described by the explorer Douglas Mawson as the windiest place on Earth following his expedition of 1911 to 1914. Because of this variation of wind speed with height, it is essential that wind measurements be made at a standard height if they are to be comparable from one location to another. As previously noted, the internationally accepted standard is 10 meters above ground level, but many wind observations, particularly historical ones, have been made at other heights, and corrections must be applied to adjust these observations to the standard height. The process of adjusting wind speeds from one height to another is straightforward under the assumption of a logarithmic wind profile, but it becomes more complicated when the atmospheric stability departs from neutral conditions, as is often the case during periods of strong surface heating or cooling. The measurement and classification of wind speed is, as may by now be apparent, a subject of considerable breadth and not inconsiderable tedium, encompassing as it does elements of physics, mathematics, engineering, history, and bureaucratic standardization. It is a subject that has occupied the attention of scientists, sailors, engineers, and administrators for centuries, and it continues to be of importance in the modern era for purposes ranging from weather forecasting and aviation safety to the design of buildings and bridges and the assessment of wind energy resources. The chapters that follow will examine in exhaustive detail the various scales and classification systems that have been developed for categorizing wind speed, beginning with the most famous and widely used of all such systems, the Beaufort scale, and proceeding through the specialized scales used for tropical cyclones, tornadoes, and other intense wind phenomena, before concluding with a survey of modern measurement techniques and their applications, the Beaufort Wind Force Scale, which is, without question, the most widely recognized and historically significant system for classifying wind speed, was devised by Rear Admiral Sir Francis Beaufort of the Royal Navy in the year 1805. Although it was not officially adopted by the Admiralty until 1838, and it did not come into general use for international meteorological purposes until considerably later in the 19th century. Francis Beaufort was born on the 27th of May, 1774, in the town of Navan, County Meath, Ireland, and he entered the Royal Navy at the age of 13, serving as a midshipman aboard various vessels and participating in a number of engagements during the French Revolutionary Wars and the Napoleonic Wars. He was wounded on several occasions, most seriously during the capture of the Spanish ship San Joseph at the Battle of Cape St. Vincent in 1797, and again in 1800 when he was shot and seriously injured while surveying the coast of Turkey. It was during his long career at sea that Beaufort developed his keen interest in meteorological observation and the systematic recording of weather conditions, and it was this interest that led him to devise his wind force scale, which he first recorded in his personal journal on the 13th of January, 1806. The original Beaufort scale was a purely descriptive system that related wind force to its effects upon the sails and rigging of a fully rigged man-of-war of the period, with 13 categories numbered from 0 to 12. Force 0 represented a complete calm, while Force 12 represented a hurricane, and the intermediate forces were described in terms of the amount of sail that such a vessel could carry under the prevailing conditions. The scale was entirely qualitative and made no reference to specific wind speeds, as reliable anemometers were not yet in widespread use aboard ships. The adoption of the Beaufort scale by the Royal Navy in 1838 was largely due to the influence of Captain Robert Fitzroy, who would later become the first director of what is now the Met Office, and who was a strong advocate for standardized meteorological observation at sea. Fitzroy made the use of the Beaufort scale compulsory for all log entries aboard Royal Navy vessels, and this requirement ensured that a vast body of comparable wind observations was accumulated over the following decades. The scale was subsequently adopted by the International Meteorological Committee in 1874, and it became the standard international scale for reporting wind force at sea, a status it retains to this day under the auspices of the World Meteorological Organization. Over the course of the 19th and 20th centuries, the Beaufort scale was modified and refined on numerous occasions to adapt it to changing circumstances and to incorporate quantitative wind speed equivalents. The original descriptions relating to the sails of a man-of-war became obsolete as sailing vessels gave way to steam-powered ships, and new descriptions based on the appearance of the sea surface were developed. In addition, a parallel set of descriptions was created for use on land, relating wind force to its effects upon trees, buildings, and other terrestrial features. The wind speed equivalents currently associated with each Beaufort force number were established through extensive research and were formally adopted by the World Meteorological Organization in 1970, based on work carried out by a number of investigators, including C. F. Bowers and others. Beaufort Force 0 is designated as calm and corresponds to wind speeds of less than 1 knot, which is equivalent to less than 0.3 meters per second or less than 1 kilometer per hour. Under these conditions, the sea surface is mirror-like and completely smooth, resembling a sheet of glass, and smoke from a chimney or other source rises vertically without any perceptible deflection. The air is utterly still, and there is no discernible movement of leaves, flags, or any other wind indicators. This condition is relatively uncommon over the open ocean, but occurs with some frequency over land, particularly during clear nights when radiative cooling produces a strong temperature inversion near the surface that suppresses vertical mixing and horizontal air movement. Beaufort Force 1 is designated as light air and corresponds to wind speeds of 1 to 3 knots, or 0.3 to 1.5 meters per second, or 1 to 5 kilometers per hour. The sea surface is characterized by small ripples with the appearance of scales, but without any foam crusts. On land, the direction of the wind may be indicated by the drift of smoke, but wind vanes are generally not responsive to such light winds. Leaves may occasionally stir slightly, but there is no perceptible movement of larger objects. Beaufort Force 2 is designated as a light breeze and corresponds to wind speeds of 4 to 6 knots, or 1.6 to 3.3 meters per second, or 6 to 11 kilometers per hour. Small wavelets begin to appear on the sea surface, with crests that have a glassy appearance and do not break. On land, the wind can be felt on the face, leaves rustle softly, and ordinary wind vanes begin to respond to the wind and indicate its direction. Flags may stir slightly, but do not extend fully from the flagpole. Beaufort Force 3 is designated as a gentle breeze and corresponds to wind speeds of 7 to 10 knots, or 3.4 to 5.4 meters per second, or 12 to 19 kilometers per hour. Large wavelets appear on the sea surface and crests begin to break, producing scattered whitecaps. There may be a few white foam patches visible on the water. On land, leaves and small twigs are in constant motion, and light flags are extended from the flagpole. The wind is sufficient to move light objects such as paper and to cause the leaves of deciduous trees to flutter audibly. Beaufort Force 4 is designated as a moderate breeze and corresponds to wind speeds of 11 to 16 knots, or 5.5 to 7.9 meters per second, or 20 to 28 kilometers per hour. The sea surface exhibits small waves with frequent whitecaps, and the waves are becoming longer in wavelength. On land, dust and loose paper are raised from the ground, and small branches of trees begin to move. Flags flutter and extend fully from the flagpole, and the wind is strong enough to be felt as a steady pressure against the body when walking. Beaufort Force 5 is designated as a fresh breeze and corresponds to wind speeds of 17 to 21 knots, or 8.0 to 10.7 meters per second, or 29 to 38 kilometers per hour. Moderate waves of some length develop on the sea surface, with many whitecaps and a chance of some spray. On land, small trees in leaf begin to sway, and crested wavelets form on inland waters, such as lakes and ponds. The wind is sufficient to cause some inconvenience when walking against it, and loose objects that are not secured may be blown about. Beaufort Force 6 is designated as a strong breeze and corresponds to wind speeds of 22 to 27 knots, or 10.8 to 13.8 meters per second, or 39 to 49 kilometers per hour. Large waves begin to form on the sea surface, with extensive white foam crests and some spray. On land, large branches of trees are in motion. Whistling is heard in overhead wires and other exposed structures, and umbrellas are used with considerable difficulty. It becomes distinctly unpleasant to walk against the wind, and the noise of the wind becomes a persistent background sound. Beaufort Force 7 is designated as a near gale or moderate gale and corresponds to wind speeds of 28 to 33 knots, or 13.9 to 17.1 meters per second, or 50 to 61 kilometers per hour. The sea surface is characterized by heaped waves, with foam from breaking waves beginning to be blown in streaks along the direction of the wind. On land, whole trees are in motion, and it is somewhat difficult to walk against the wind. Inconvenience is felt when walking, and there may be minor structural damage to poorly maintained buildings, such as the loss of roof tiles or the breaking of small branches. Beaufort Force 8 is designated as a gale or fresh gale and corresponds to wind speeds of 34 to 40 knots, or 17.2 to 20.7 meters per second, or 62 to 74 kilometers per hour. Moderately high waves of greater length develop on the sea surface, with edges of crests beginning to break into spindrift, and well-marked streaks of foam are blown along the direction of the wind. On land, twigs and small branches are broken off trees, and it is generally difficult to walk against the wind. Progress on foot is significantly impeded, and loose objects may be blown considerable distances. Some structural damage to buildings may occur, including the loss of chimney pots and roof slates. Beaufort Force 9 is designated as a strong gale or severe gale and corresponds to wind speeds of 41 to 47 knots, or 20.8 to 24.4 meters per second, or 75 to 88 kilometers per hour. High waves develop on the sea surface, with dense streaks of foam along the wind direction. The sea begins to roll, and spray may affect visibility. On land, slight structural damage occurs to buildings, with chimney pots, roof tiles, and aerials being removed. Branches of moderate size are broken from trees, and some small trees may be blown over. Garden furniture and other unsecured outdoor objects are displaced. Beaufort Force 10 is designated as a storm or whole gale and corresponds to wind speeds of 48 to 55 knots, or 24.5 to 28.4 meters per second, or 89 to 102 kilometers per hour. Very high waves with long overhanging crests develop on the sea surface, and the resulting foam, in great patches, is blown in dense white streaks along the direction of the wind. The surface of the sea takes on a white appearance overall, and the tumbling of the sea becomes heavy and shock-like. Visibility is reduced by spray. On land, trees are uprooted and considerable structural damage occurs to buildings. This force of wind is seldom experienced inland, but is encountered with some regularity over the open oceans of the higher latitudes, particularly in the Southern Ocean. Beaufort Force 11 is designated as a violent storm and corresponds to wind speeds of 56 to 63 knots, or 28.5 to 32.6 meters per second, or 103 to 117 kilometers per hour. Exceptionally high waves develop on the sea surface, and the sea is completely covered with long white patches of foam lying along the direction of the wind. Everywhere the edges of the wave crests are blown into froth, and visibility is seriously affected by spray. On land, widespread damage occurs to buildings and vegetation, and only the sturdiest of structures remain undamaged. Trees are uprooted or snapped, and large objects may be displaced considerable distances by the wind. Beaufort Force 12 is designated as hurricane force and corresponds to wind speeds of 64 knots or greater, which is equivalent to 32.7 meters per second or greater, or 118 kilometers per hour or greater. The air is filled with foam and spray, the sea is completely white with driving spray and visibility is very seriously reduced. On land, devastation is widespread, with severe and extensive damage to buildings, infrastructure, and vegetation. This force of wind is associated with tropical cyclones, the most intense extratropical cyclones, and other extreme weather events. The original Beaufort scale terminated at force 12, which was described simply as that which no canvas could withstand, a description that was vivid in its simplicity and entirely appropriate for the age of sail in which the scale was conceived. It should be noted that the Beaufort scale, in its standard form with forces 0 through 12, was designed primarily for maritime use and was adapted for land use only subsequently. The correspondence between sea state descriptions and wind speed is well established for the open ocean, but may be less reliable in coastal waters, enclosed seas, and other locations where the fetch, depth, and other factors affect wave development. Similarly, the land descriptions are somewhat subjective and may vary depending on the type of vegetation, construction standards, and other local factors. Nevertheless, the Beaufort scale has proven to be an extraordinarily useful and durable system for categorizing wind conditions, and its widespread adoption and long history of use have made it one of the most successful classification schemes in all of meteorology. The history of the Beaufort scale's adoption is itself a study in the gradual standardization of scientific observation. After its initial adoption by the Royal Navy in 1838, the scale was taken up by other maritime nations, and efforts were made to ensure that all observers were using the same criteria for assigning force numbers. The International Meteorological Conference held in Brussels in 1853, at which representatives from 10 maritime nations gathered under the chairmanship of Lieutenant Matthew Fontaine Maury of the United States Navy, played an important role in promoting the international adoption of the Beaufort scale, although the process of achieving full standardization took many more decades. The association of specific wind speed ranges with each Beaufort force number was a development that occurred gradually over the late 19th and early 20th centuries. Various researchers and national meteorological services proposed different equivalences, and there was considerable disagreement about the correct relationship between Beaufort force and wind speed. The matter was complicated by the fact that the original Beaufort scale was defined in terms of its effects rather than in terms of measurable quantities, and different observers might assign different force numbers to the same wind speed depending on their interpretation of the descriptive criteria. The wind speed equivalents that are used today were developed through a combination of theoretical analysis and empirical measurement, drawing on data from anemometers exposed alongside trained observers making Beaufort estimates, and they were formally adopted by the World Meteorological Organization in 1970. In 1946, the International Meteorological Organization extended the Beaufort scale beyond force 12 to include 5 additional categories, forces 13 through 17. For use in classifying the extremely high winds associated with tropical cyclones in the western Pacific. This extended scale is used primarily by the China Meteorological Administration and the meteorological services of adjacent countries, and it is not in general international use. Force 13 corresponds to wind speeds of 72 to 80 knots, or 37.0 to 41.4 meters per second, or 134 to 149 kilometers per hour. Force 14 corresponds to wind speeds of 81 to 89 knots, or 41.5 to 46.1 meters per second, or 150 to 166 kilometers per hour. Force 15 corresponds to wind speeds of 90 to 99 knots, or 46.2 to 50.9 meters per second, or 167 to 183 kilometers per hour. Force 16 corresponds to wind speeds of 100 to 108 knots, or 51.0 to 56.0 meters per second, or 184 to 201 kilometers per hour. Force 17 corresponds to wind speeds of 109 to 119 knots, or 56.1 to 61.2 meters per second, or 202 to 220 kilometers per hour. These extended categories were introduced because the original scale, with its upper limit of force 12 corresponding to 64 knots and above, provided insufficient discrimination among the varying intensities of tropical cyclones, some of which produce sustained winds well in excess of 150 knots. However, the extended Beaufort scale has not been adopted by most international meteorological services, which prefer to use specialized tropical cyclone intensity scales, such as the Saffir-Simpson hurricane wind scale used in the North Atlantic and eastern North Pacific basins, for classifying the winds of tropical cyclones. The Beaufort scale remains in operational use today for reporting wind conditions at sea, and it is still widely taught in maritime training courses and included in nautical almanacs and sailing handbooks. Weather forecasts for maritime areas frequently refer to Beaufort force numbers and the terminology of the scale, with its familiar designations of calm, light breeze, moderate gale, storm, and hurricane force, has become deeply embedded in the language of seafaring and meteorology. The scale's enduring popularity is a testament to the elegance and practicality of Beaufort's original concept, which was to provide a simple, standardized system for describing wind conditions that could be used consistently by all observers regardless of whether they had access to measuring instruments. Francis Beaufort himself went on to have a distinguished career in the Royal Navy, serving as hydrographer of the Navy from 1829 to 1855, during which period he oversaw a vast program of hydrographic surveying that greatly expanded the world's stock of accurate nautical charts. He was made a Knight Commander of the Order of the Bath in 1848 and was elected a Fellow of the Royal Society. He died on the 17th of December, 1857, at the age of 83, and his legacy lives on in the wind scale that bears his name, as well as in the Beaufort Sea in the Arctic Ocean, which was named in his honor by his friend and colleague, Sir John Franklin. The application of the Beaufort scale to land observations, which is now standard practice at weather stations worldwide, was formalized in the early 20th century through the work of George Simpson, who later became director of the Meteorological Office in the United Kingdom. Simpson developed a set of land-based criteria for each Beaufort force number that could be used by observers who did not have access to an anemometer, and these criteria, with various modifications, are still included in the World Meteorological Organization's guidelines for surface weather observation. The land-based criteria are necessarily somewhat more subjective than the sea state criteria, as they depend on the types of vegetation and structures present at the observation site, but they provide a useful guide for estimating wind speed in the absence of instrumental measurements. It is perhaps worth noting that the Beaufort scale, for all its practical utility and historical significance, is not a linear scale, which is to say that the wind speed increment associated with each step increase in Beaufort force number is not constant. The wind speeds corresponding to the lower force numbers are separated by relatively small increments, while the higher force numbers span increasingly large wind speed ranges. This nonlinearity reflects the fact that the scale was originally defined in terms of the wind's effects rather than its speed, and the relationship between wind speed and the force exerted on objects is quadratic rather than linear, since the aerodynamic drag force is proportional to the square of the wind speed. An empirical formula relating Beaufort force number b to wind speed via knots was proposed by various investigators and is approximately given by v equals 0.836 times b to the power of 3/2. Although this formula is only an approximation and does not precisely reproduce the officially adopted wind speed equivalents for all force numbers, the Beaufort scale has also been adapted for specialized uses beyond its original maritime and general meteorological applications. For example, a version of the scale for use in estimating wind speeds from the damage to vegetation was developed by researchers studying the effects of tropical cyclones on forests, and similar adaptations have been made for use in assessing wind damage to agricultural crops. These specialized versions of the scale illustrate the fundamental versatility of Beaufort's original concept, which is simply to relate wind speed to observable effects in a systematic and reproducible manner. In the modern era, the Beaufort scale coexists with a variety of other wind classification systems that have been developed for specific purposes, and it is to these other systems that attention shall now be turned in the subsequent portion of this discussion. The Beaufort scale remains the most general purpose and widely used of all wind classification systems, but the specialized demands of tropical cyclone forecasting, tornado damage assessment, and other applications have given rise to additional scales that provide more detailed and nuanced classifications of extreme wind events. These scales, their histories, and their technical specifications will be examined in due course, at a pace that is, one hopes, conducive to the gradual onset of drowsiness. The classification of winds associated with tropical cyclones requires a degree of precision and specificity that the general-purpose Beaufort scale, with its single hurricane force category of Force 12 and above, cannot provide. For this reason, specialized intensity scales have been developed for tropical cyclones in various ocean basins, and the most widely known of these is the Saffir-Simpson Hurricane Wind Scale, which is used by the National Hurricane Center of the United States for classifying hurricanes in the North Atlantic Ocean and the eastern North Pacific Ocean. This scale was originally developed in the early 1970s by the civil engineer Herbert Saffir and the meteorologist Robert Simpson, who was at that time the director of the National Hurricane Center. And it was initially conceived as a more comprehensive hurricane disaster potential scale that incorporated not only wind speed, but also central pressure and storm surge. However, in 2010, the scale was simplified to focus exclusively on maximum sustained wind speed, and the storm surge component was removed, on the grounds that storm surge depends on a complex combination of factors beyond wind speed alone. The Saffir-Simpson Hurricane Wind Scale divides hurricanes into 5 categories based on maximum sustained wind speed, where sustained wind speed is defined as the 1-minute average wind speed at a height of 10 meters above the surface. It is important to note that this definition of sustained wind speed differs from the standard used by most other national meteorological services, which employ a 10-minute averaging period. And this difference in averaging period means that wind speeds reported by the National Hurricane Center are typically somewhat higher than those that would be reported by other services for the same storm, because the shorter averaging period captures more of the peak wind fluctuations. Category 1 on the Saffir-Simpson scale corresponds to maximum sustained winds of 64 to 82 knots, which is equivalent to 74 to 95 miles per hour. Or 119 to 153 kilometers per hour, or 33 to 42 meters per second. Hurricanes of this intensity are expected to produce some damage to well-constructed frame homes, including damage to roofing materials, vinyl siding, and gutters. Large branches of trees may snap, and shallowly rooted trees may be toppled. Extensive damage to power lines and poles is likely, resulting in power outages that may last from several days to a few weeks. Category 2 corresponds to maximum sustained winds of 83 to 95 knots, or 96 to 110 miles per hour, or 154 to 177 kilometers per hour, or 43 to 49 meters per second. Hurricanes of this intensity are expected to cause extensive damage to well-constructed frame homes, with the potential for major roof and siding damage. Many shallowly rooted trees will be snapped or uprooted, blocking roads and causing additional damage. Near total power loss is expected, with outages potentially lasting from several weeks to several months. Category 3 corresponds to maximum sustained winds of 96 to 112 knots, or 111 to 129 miles per hour, or 178 to 208 kilometers per hour, or 50 to 58 meters per second. A hurricane of Category 3 or higher is classified as a major hurricane, and such storms are expected to cause devastating damage to well-built frame homes, including removal of roof decking and gable ends. Many trees will be snapped or uprooted, and electricity and water supplies will be unavailable for days to weeks after the storm passes. Category 4 corresponds to maximum sustained winds of 113 to 136 knots, or 130 to 156 miles per hour, or 209 to 251 kilometers per hour, or 58 to 70 meters per second. Catastrophic damage is expected, with well-built frame homes suffering severe damage, including the loss of most of the roof structure and some exterior walls. Most trees will be snapped or uprooted, and power poles will be downed. Fallen trees and power poles will isolate residential areas, and power outages will last for weeks to possibly months. Most of the affected area will be uninhabitable for weeks or months. Category 5, the highest category on the Saffir-Simpson scale, corresponds to maximum sustained winds of 137 knots or greater, or 157 miles per hour or greater, or 252 kilometers per hour or greater, or 70 meters per second or greater. A Category 5 hurricane is expected to cause catastrophic damage, with a high percentage of frame homes being destroyed, including total roof failure and wall collapse. Fallen trees and power poles will isolate residential areas, and power outages will last for weeks to possibly months. Most of the affected area will be uninhabitable for weeks or months. Only a small number of tropical cyclones in the historical record have reached Category 5 intensity, although notable examples include Hurricane Allen in 1980, Hurricane Gilbert in 1988, Hurricane Andrew in 1992, Hurricane Mitch in 1998, and Hurricane Dorian in 2019. The strongest tropical cyclone ever recorded in terms of maximum sustained wind speed is generally considered to be Typhoon Tip, which occurred in the western North Pacific in October 1979 and was estimated to have reached maximum sustained winds of 165 knots, or 190 miles per hour, or 305 kilometers per hour. However, it should be noted that wind speed estimates for tropical cyclones, particularly those in the open ocean far from land-based observation stations, are subject to considerable uncertainty, as they are often based on indirect methods such as the Dvorak technique, which estimates tropical cyclone intensity from the appearance of the storm in satellite imagery. The classification of tornadoes, which are among the most violent and destructive of all atmospheric phenomena, has followed a somewhat different trajectory from the classification of tropical cyclone winds. Tornadoes are characterized by extremely intense, highly localized vortices with diameters typically ranging from a few tens of meters to about 2 kilometers, and they produce the highest wind speeds that occur anywhere in the Earth's atmosphere, with estimated maximum winds in the most intense tornadoes exceeding 300 knots or 150 meters per second. Because of their small scale, short duration, and extreme destructive power, tornadoes are exceptionally difficult to measure directly with conventional anemometers. And most tornado intensity estimates are based not on measured wind speeds, but on assessments of the damage they produce. The original Fujita scale, also known as the F scale, was developed in 1971 by Tetsuya Theodore Fujita, a Japanese-American meteorologist at the University of Chicago, who is sometimes referred to as Mr. Tornado for his pioneering research into tornado dynamics and damage. The Fujita scale classified tornadoes into 6 categories, F0 through F5, based on the estimated wind speed required to produce the observed damage. F0, designated as light damage, corresponded to estimated wind speeds of 40 to 72 miles per hour, or 64 to 116 kilometers per hour. F1, designated as moderate damage, corresponded to 73 to 112 miles per hour, or 117 to 180 kilometers per hour. F2, designated as considerable damage, corresponded to 113 to 157 miles per hour, or 181 to 253 kilometers per hour. F3, designated as severe damage, corresponded to 158 to 206 miles per hour, or 254 to 332 kilometers per hour. F4, designated as devastating damage, corresponded to 207 to 260 miles per hour, or 333 to 418 kilometers per hour. F5, designated as incredible damage, corresponded to 261 to 318 miles per hour, or 419 to 512 kilometers per hour. The original Fujita scale, while groundbreaking in its conception, was found over time to have several significant shortcomings. The wind speed ranges assigned to each category were based largely on theoretical estimates and limited observational data, and subsequent research suggested that the wind speeds required to produce the damage described for each category were in many cases considerably lower than those specified by the original scale. This meant that many tornadoes were being assigned higher wind speed estimates than were actually warranted by the observed damage, leading to a systematic overestimation of tornado wind speeds. To address these issues, the Enhanced Fujita Scale, commonly abbreviated as the F scale, was developed by a team of meteorologists and wind engineers led by James McDonald of Texas Tech University and implemented by the National Weather Service of the United States on the 1st of February, 2007. The Enhanced Fujita Scale retains the same basic structure of 6 categories, now designated EF0 through EF5, but it incorporates a much more detailed and rigorous system for estimating wind speeds from damage observations. The Enhanced Fujita Scale is based on 20 damage indicators, which represent different types of structures and objects that may be affected by tornado winds, including 1- and 2-family residences, manufactured homes, apartment and condominium buildings, motels and hotels, small retail buildings, small professional buildings, shopping malls, large shopping malls, automobile showrooms, schools, hospitals, warehouses, grain storage bins, churches, strip malls, large isolated retail, buildings, electric transmission lines, freestanding towers, hardwood trees, softwood trees, and various other categories. For each damage indicator, a series of degrees of damage is defined, ranging from the threshold of visible damage to complete destruction, and each degree of damage is associated with an expected wind speed, an upper bound wind speed, and a lower bound wind speed. EF0 on the enhanced Fujita scale corresponds to estimated 3-second gust wind speeds of 65 to 85 miles per hour, or 105 to 137 kilometers per hour. Damage at this level is characterized as light, and it includes the breaking of branches from trees, damage to chimneys, and the removal of surface material from some roofs. EF1 corresponds to estimated gust wind speeds of 86 to 110 miles per hour, or 138 to 178 kilometers per hour. Moderate damage is expected, including the peeling of surface material from roofs, mobile homes being overturned or seriously damaged, and moving automobiles being pushed off roads. EF2 corresponds to estimated gust wind speeds of 111 to 135 miles per hour, or 179 to 218 kilometers per hour. Considerable damage is expected, with roofs being torn off frame houses, mobile homes being completely destroyed, large trees being snapped or uprooted, and light object missiles being generated. EF3 corresponds to estimated gust wind speeds of 136 to 165 miles per hour, or 219 to 266 kilometers per hour. Severe damage is expected, with roofs and some walls being torn off well-constructed houses, trains being overturned, most trees in forested areas being uprooted, and heavy cars being lifted and thrown. EF4 corresponds to estimated gust wind speeds of 166 to 200 miles per hour, or 267 to 322 kilometers per hour. Devastating damage is expected, with well-constructed houses being completely leveled, structures with weak foundations being blown some distance, and cars and other large objects being thrown considerable distances to generate dangerous missiles. EF5 corresponds to estimated gust wind speeds of greater than 200 miles per hour, or greater than 322 kilometers per hour. The damage at this level is described as incredible, with strong frame houses being lifted from foundations and carried considerable distances to be disintegrated. Automobile-sized missiles being generated and carried through the air for distances of 100 meters or more, trees being debarked, and steel-reinforced concrete structures being critically damaged. The Toro Tornado Intensity Scale, which is used primarily in the United Kingdom and some other European countries, was developed by Terence Meaden of the Tornado and Storm Research Organization, from which the acronym TORO is derived. in 1972. The Toro scale is more finely graduated than the Fujita or enhanced Fujita scales, with 11 categories designated T0 through T10, and it was designed to be applicable to the generally weaker tornadoes that occur in the United Kingdom and Europe, as well as to the more intense tornadoes found in the United States. T0 corresponds to wind speeds of 39 to 54 miles per hour, while T10 corresponds to wind speeds in excess of 261 miles per hour. The Toro scale has not been widely adopted outside of Europe and is not recognized by the World Meteorological Organization as a standard classification system. An important distinction that must be understood in the context of wind speed classification is the difference between sustained winds and gusts. A sustained wind speed is the average wind speed measured over a specified period of time, typically 1 minute in the United States and 10 minutes in most other countries, while a gust is a brief, sudden increase in wind speed that lasts only a few seconds. The ratio of gust speed to sustained wind speed, known as the gust factor, varies depending on the roughness of the terrain, the height of measurement, and the atmospheric stability. But typical values range from approximately 1.3 to 1.5 over open terrain at a height of 10 meters. This means that the peak gust speed during a period of sustained high winds may be 30 to 50% greater than the sustained wind speed. The difference between sustained winds and gusts is of considerable practical importance in wind speed classification because some scales, such as the Beaufort scale and the Saffir-Simpson hurricane wind scale, are based on sustained wind speeds, while others, such as the enhanced Fujita scale, are based on estimated gust wind speeds. This difference in the underlying wind speed metric means that direct comparisons between the scales must be made with care, and the appropriate gust factor must be applied when converting between sustained and gust wind speeds. It is not uncommon for media reports and even some technical publications to confuse sustained and gust wind speeds, leading to inaccurate comparisons and misunderstandings about the relative intensity of different wind events. The concept of wind chill, which quantifies the cooling effect of wind on exposed human skin, is another aspect of wind that has been the subject of classification and standardization efforts. The wind chill equivalent temperature, often simply called the wind chill, is defined as the temperature that would produce the same rate of heat loss from exposed skin under calm conditions as the actual combination of air temperature and wind speed. The current wind chill formula used in the United States and Canada was adopted in 2001 and is based on research conducted by Randall Oskrzewski and Maurice Bluestein, who used a model of heat loss from the human face under various combinations of temperature and wind speed. The formula gives the wind chill temperature in degrees Fahrenheit as 35.74 plus 0.6215 times the air temperature minus 35.75 times the wind speed raised to the power 0.16 plus 0.4275 times the air temperature times the wind speed raised to the power 0.16, where the air temperature is in degrees Fahrenheit and the wind speed is in miles per hour. The world record for the highest surface wind speed ever reliably measured is generally attributed to a gust of 253 miles per hour, or 408 kilometers per hour, or 113 meters per second. Recorded on the 3rd of May, 1999, by a mobile Doppler radar unit operated by researchers from the University of Oklahoma during the Bridge Creek Moore tornado in Oklahoma. However, this measurement was made by radar rather than by a conventional anemometer and represents a Doppler velocity that may not be directly comparable to a surface wind speed measurement. The highest surface wind speed measured by a conventional anemometer at a fixed weather station is 372 kilometers per hour, or 231 miles per hour, or 103 meters per second. Recorded on the 10th of April, 1996, during Tropical Cyclone Olivia on Barrow Island, off the coast of Western Australia. This measurement supplanted the previous record of 372 kilometers per hour recorded atop Mount Washington in New Hampshire on the 12th of April, 1934, which held the record for more than 60 years. The highest sustained wind speed ever measured in a tropical cyclone by aircraft reconnaissance is generally considered to be 165 knots, or 190 miles per hour. Recorded in Typhoon Tip in October 1979 and in Hurricane Patricia in October 2015. Hurricane Patricia, which formed in the eastern North Pacific, underwent an extraordinary period of rapid intensification, with its maximum sustained winds increasing from 85 miles per hour to 215 miles per hour in just 24 hours, making it one of the most rapidly intensifying tropical cyclones ever observed. The central pressure of Hurricane Patricia at peak intensity was estimated at 872 hectopascals, making it the most intense tropical cyclone ever recorded in the Western Hemisphere in terms of central pressure. The measurement and recording of extreme wind events is complicated by the fact that the instruments used to measure wind speed may themselves be damaged or destroyed by the very winds they are attempting to measure. Many of the highest wind speeds associated with tornadoes and intense tropical cyclones are estimated rather than directly measured, because anemometers and other instruments are unable to withstand the extreme conditions. The development of mobile Doppler radar systems, which can measure wind speeds remotely from a distance of several kilometers, has provided a valuable tool for estimating wind speeds in tornadoes and other severe convective storms. But these measurements are subject to their own uncertainties and limitations. It is also worth mentioning several notable named winds from around the world that have been recognized and classified by various meteorological traditions over the centuries. The Mistral, which blows from the northwest through the Rhône Valley of southern France, is a cold, dry wind that can reach speeds of 100 kilometers per hour or more and may persist for several days at a time, typically occurring when a high-pressure system is centered over the Bay of Biscay and a low-pressure system is located over the Gulf of Genoa. The Bora, which is a cold, gusty wind that descends from the mountains along the eastern coast of the Adriatic Sea, can produce gusts exceeding 200 kilometers per hour in extreme cases, with the city of Trieste being particularly well known for its exposure to this wind. The Sirocco, which originates over the Sahara Desert and blows northward across the Mediterranean, is a hot, dry wind that can carry large quantities of dust and sand, sometimes depositing a thin layer of reddish-brown dust on surfaces as far north as Central Europe. The Chinook, which is a warm, dry wind that descends the eastern slopes of the Rocky Mountains in North America, is a type of foehn wind that can produce remarkable temperature increases in a very short period of time, with temperature rises of 20 to 30 degrees Celsius in the space of a few hours being documented in locations such as Rapid City, South Dakota, and Lethbridge, Alberta. The harmattan, which blows from the northeast across West Africa during the dry season from November to March, is a hot, dusty wind that carries fine particles of sand and dust from the Sahara, reducing visibility to as little as 1 kilometer and creating a distinctive hazy atmosphere. The Santa Ana winds of Southern California are hot, dry winds that blow from the interior deserts through the mountain passes and canyons toward the coast, and they are associated with an increased risk of wildfire due to their low humidity and high speeds, which can exceed 100 kilometers per hour in the most exposed locations. The Zonda, which is the South American equivalent of the Chinook, descends the eastern slopes of the Andes in Argentina and can produce similarly dramatic temperature increases. These named winds, each with their characteristic speeds, directions, temperatures, and seasonal patterns, represent a rich tradition of wind observation and classification that predates the formal scientific scales by many centuries and continues to be relevant to the daily lives of people living in the affected regions. The recording of wind speed records is maintained by various national and international organizations, including the World Meteorological Organization, which maintains official records of weather and climate extremes. The process of verifying and certifying a new world record wind speed is rigorous and time-consuming, involving detailed examination of the instruments used, the conditions under which the measurement was made, and the quality of the data record. In some cases, previously accepted records have been revised or withdrawn upon closer examination, as was the case with certain historical wind speed measurements that were found to have been affected by instrumental errors or non-standard exposure conditions. The diversity of wind classification scales in use around the world reflects the diverse purposes for which wind speed information is needed, ranging from maritime navigation and weather forecasting to structural engineering and disaster preparedness. Each scale has been designed with a particular application in mind, and the thresholds and categories of each scale reflect the specific concerns of the users for whom it was developed. The Beaufort scale, with its origins in the Age of Sail, is oriented toward the practical needs of mariners. The Saffir-Simpson scale is designed to communicate the potential destructive impact of hurricanes to the general public and to emergency managers. The Enhanced Fujita scale is a forensic tool for assessing tornado intensity after the fact based on damage surveys. and the various other scales and classification systems that exist serve their own specialized purposes in their respective domains. The coexistence of these multiple scales, while sometimes confusing, reflects the fundamental complexity of wind as a natural phenomenon and the diverse ways in which it affects human activities and the built environment. The measurement of wind speed and direction in the modern era has been transformed by the development of a wide variety of sophisticated instruments and techniques that go far beyond the mechanical cup anemometers and wind vanes that served as the primary tools of wind observation for more than a century. While the cup anemometer remains in widespread use at surface weather stations around the world, it has been supplemented and in some applications replaced by instruments that offer superior accuracy, faster response times, greater reliability, and the ability to measure wind at locations and altitudes that are inaccessible to conventional surface-based instruments. The sonic anemometer, also known as an ultrasonic anemometer, is one of the most important modern instruments for measuring wind speed and direction. The operating principle of the sonic anemometer is based on the measurement of the transit time of ultrasonic pulses traveling between pairs of transducers. When an ultrasonic pulse travels in the same direction as the wind, its transit time is reduced, and when it travels against the wind, its transit time is increased. By measuring the transit times in both directions along each axis and computing the difference, the component of wind speed along that axis can be determined with high precision. A typical three-dimensional sonic anemometer employs 3 pairs of transducers arranged along 3 noncoplanar axes, enabling the simultaneous measurement of the 3 components of the wind vector at sampling rates of up to 100 Hz or more. The advantages of the sonic anemometer over the cup anemometer are numerous and substantial. Because the sonic anemometer has no moving parts, it is not subject to the mechanical wear, bearing friction, and inertia effects that limit the performance of cup anemometers. The response time of a sonic anemometer is essentially instantaneous, limited only by the transit time of the ultrasonic pulses, which is on the order of a few milliseconds, compared to the response time of a cup anemometer, which may be on the order of several seconds, depending on the size and inertia of the cup assembly. Sonic anemometers can measure 3-dimensional wind vectors, including the vertical component, which is particularly important for studies of atmospheric turbulence, boundary layer processes, and the exchange of heat, moisture, and momentum between the surface and the atmosphere. The accuracy of a well-calibrated sonic anemometer is typically better than plus or minus 1% for wind speed and plus or minus 1 degree for wind direction, which is considerably better than the accuracy achievable with conventional mechanical instruments. The sonic anemometer is widely used in research applications, including micrometeorological studies, eddy covariance flux measurements, and wind tunnel testing. And it has also been adopted for operational use at an increasing number of weather stations and airports. The cost of sonic anemometers has decreased substantially over the past 2 decades, making them accessible to a wider range of users, although they remain more expensive than cup anemometers and are somewhat more sensitive to the effects of precipitation, which can attenuate the ultrasonic signal and introduce errors in the measurements. Doppler radar represents another major advance in wind measurement technology, providing the ability to measure winds remotely over large areas and at multiple altitudes simultaneously. The Doppler radar measures the velocity of targets moving toward or away from the radar by detecting the frequency shift, known as the Doppler shift, in the microwave radiation that is backscattered by raindrops, ice particles, insects, or other targets in the atmosphere. The velocity measured by the radar is the radial component of the target's velocity along the radar beam, and by scanning the radar beam through a series of elevation and azimuth angles, a three-dimensional picture of the wind field can be constructed. The development of Doppler weather radar for operational meteorological use began in the 1960s and 1970s, and the first operational Doppler radar network in the United States, known as the WSR 88D or NEXRAD system, was deployed beginning in 1988. The NEXRAD network currently consists of approximately 160 radar installations covering the contiguous United States, Alaska, Hawaii, and various overseas territories and military installations. Each NEXRAD radar operates at a frequency of approximately 2.7 to 3.0 GHz, corresponding to a wavelength of about 10 centimeters, and it can detect precipitation and measure radial velocities at ranges of up to 230 kilometers. The velocity resolution of the NEXRAD radar is approximately 1 meter per second, and the spatial resolution depends on the range, but is typically on the order of 250 meters to 1 kilometer. Doppler radar has proven to be an invaluable tool for detecting and tracking severe weather phenomena, including mesocyclones, tornado vortex signatures, and downbursts, all of which are characterized by distinctive patterns in the radial velocity field. The ability of Doppler radar to detect rotation within thunderstorms has significantly improved the lead time of tornado warnings, from an average of about 5 minutes before the deployment of NEXRAD to approximately 13 minutes afterward. And this improvement in warning lead time has been credited with saving numerous lives. Doppler LiDAR, which operates on the same basic principle as Doppler radar, but uses laser light rather than microwave radiation, provides even higher spatial resolution and is particularly useful for measuring winds in clear air conditions when there are insufficient targets for microwave radar. A typical Doppler LiDAR system emits pulses of laser light at a wavelength of approximately 1.5 micrometers and measures the Doppler shift of light backscattered by aerosol particles and molecules in the atmosphere. The spatial resolution of a Doppler LiDAR can be as fine as a few meters, and the temporal resolution can be on the order of seconds, making it an excellent tool for studying boundary layer winds, turbulence, and wind shear in the vicinity of airports. Doppler LiDAR systems have been deployed at a number of major airports around the world for the purpose of detecting and warning of wind shear conditions that pose a hazard to aircraft during takeoff and landing. Satellite-based scatterometry provides yet another means of measuring wind speed and direction, this time over the vast expanses of the open ocean where conventional surface-based measurements are sparse or non-existent. A scatterometer is a radar instrument carried aboard an orbiting satellite that measures the amount of microwave radiation backscattered by the ocean surface. The roughness of the ocean surface is directly related to the wind speed, because the small-scale capillary waves and short gravity waves that are responsible for most of the microwave backscatter are generated by the local wind. By measuring the backscatter coefficient at multiple azimuth angles, both the speed and direction of the surface wind can be inferred. The first satellite scatterometer designed specifically for measuring ocean surface winds was the CSAT satellite scatterometer, launched in June 1978 aboard the CSAT satellite. Although the CSAT mission lasted only about 100 days before the satellite suffered a catastrophic power failure, it demonstrated the feasibility of satellite-based wind measurement and provided a wealth of valuable data. Subsequent scatterometer missions have included the European Remote Sensing Satellites ERS-1 and ERS-2, launched in 1991 and 1995 respectively, the NASA QuickSat satellite launched in 1999, and the Indian Oceansat-2 satellite launched in 2009. The accuracy of scatterometer wind measurements is typically about 1 to 2 meters per second for wind speed and about 20 degrees for wind direction, which is sufficient for many meteorological and oceanographic applications. Wind profiling is the process of measuring the vertical profile of wind speed and direction through the depth of the atmosphere, and it is accomplished by a variety of techniques depending on the altitude range of interest and the required spatial and temporal resolution. In the lower atmosphere, up to a height of a few kilometers, wind profiling can be carried out using radiosondes, which are instrument packages carried aloft by weather balloons and which measure wind speed and direction by tracking the position of the balloon as it ascends through the atmosphere. Radiosondes are launched twice daily at approximately 800 stations worldwide as part of the global upper air observation network coordinated by the World Meteorological Organization, and they provide wind measurements at standard pressure levels from the surface to altitudes of 20 to 30 kilometers. Wind profiler radars, which are vertically pointing or near vertically pointing Doppler radars, provide continuous measurements of the vertical wind profile at fixed locations with high temporal resolution. A wind profiler radar typically operates at frequencies in the range of 50 MHz to 1,300 MHz, and measures the Doppler shift of signals backscattered by turbulent inhomogeneities in the refractive index of the atmosphere. By pointing the beam in several directions, typically north, south, east, west, and vertical, the horizontal and vertical components of the wind can be determined at multiple heights. The height range of a wind profiler radar depends on its operating frequency. Low-frequency profilers operating near 50 MHz can measure winds up to about 20 kilometers, while higher-frequency profilers operating near 1,000 MHz are limited to a range of about 2 to 4 kilometers, but provide finer spatial resolution. Automated weather stations, which have largely replaced human observers at many locations around the world, incorporate a variety of sensors for measuring wind speed and direction along with other meteorological variables. A typical automated weather station measures wind speed using a cup anemometer or sonic anemometer, wind direction using a wind vane or sonic anemometer, air temperature using a resistance thermometer, relative humidity using a capacitive humidity sensor, atmospheric pressure using a barometric pressure sensor, precipitation using a tipping bucket rain gauge or weighing precipitation gauge, and solar radiation using a pyranometer. The data from these sensors are recorded by a data logger at intervals of typically 1 to 10 minutes and transmitted to a central data processing facility via telephone, satellite, or internet connection. The World Meteorological Organization's global observing system encompasses approximately 11,000 land-based weather stations, of which a substantial and growing proportion are automated. The automation of weather observation has brought significant benefits in terms of data quality, consistency, temporal resolution, and cost-effectiveness, but it has also introduced some challenges, particularly with regard to the measurement of weather phenomena that are difficult to detect instrumentally, such as the type and amount of cloud cover, the occurrence of fog, and the intensity of precipitation. The assessment of wind energy resources is one of the most important modern applications of wind measurement and classification, driven by the rapid growth of the wind energy industry over the past several decades. The power available in the wind is proportional to the cube of the wind speed, which means that even small differences in wind speed can have very large effects on the amount of energy that can be extracted by a wind turbine. Specifically, the power per unit area of a wind stream is given by 1/2 times the air density times the cube of the wind speed. And the fraction of this power that can actually be extracted by a wind turbine is limited by the Betz limit to a theoretical maximum of 16/27, or approximately 59.3%. Although practical wind turbines typically achieve efficiencies of 35 to 45%. Because of the cubic relationship between wind speed and available power, the accurate characterization of the wind resource at a potential wind farm site is of paramount importance for the economic viability of the project. Wind resource assessment typically involves the installation of tall meteorological masts, usually 50 to 100 meters in height, instrumented with anemometers and wind vanes at multiple heights, and the collection of wind data over a period of at least 1 year and preferably 2 to 3 years in order to capture the full range of seasonal and interannual variability in the wind resource. The data collected from these masts are then analyzed using statistical methods to characterize the wind climate at the site, including the mean wind speed, the wind speed frequency distribution, the wind direction distribution, the turbulence intensity, and the wind shear profile. The statistical distribution of wind speeds at most locations is well described by the Weibull distribution, which is a 2-parameter probability distribution characterized by a scale parameter and a shape parameter. The probability density function of the Weibull distribution gives the probability of observing a wind speed within a specified range. And the cumulative distribution function gives the probability that the wind speed is less than or equal to a given value. The scale parameter of the Weibull distribution is related to the mean wind speed and determines the overall magnitude of the wind speeds, while the shape parameter determines the breadth of the distribution. A shape parameter of approximately 2, which is known as the Rayleigh distribution, is commonly observed at many wind energy sites, but values ranging from about 1.5 to 3.5 are encountered in practice depending on the location and the local wind climate. The Weibull distribution has been found to provide a good fit to observed wind speed frequency distributions at the vast majority of locations around the world, and it is used extensively in the wind energy industry for resource assessment, energy yield estimation, and the design of wind turbines. The expected annual energy production of a wind turbine at a given site can be estimated by integrating the product of the wind turbine's power curve, which gives the electrical power output as a function of wind speed, and the Weibull probability density function over the full range of wind speeds. This calculation, while straightforward in principle, requires accurate knowledge of both the power curve and the wind speed distribution, and uncertainties in either of these quantities can lead to significant errors in the estimated energy production. Boundary layer meteorology, which is the branch of atmospheric science concerned with the properties and behavior of the lowest portion of the atmosphere, provides the theoretical framework for understanding the vertical and temporal variations of wind that are observed near the Earth's surface. The atmospheric boundary layer, also known as the planetary boundary layer, is defined as the layer of the atmosphere that is directly influenced by the presence of the Earth's surface and responds to surface forcing with a timescale of about 1 hour or less. The depth of the boundary layer varies from as little as 100 meters during stable nighttime conditions to as much as 2 to 3 kilometers during convective daytime conditions over land. Within the boundary layer, the wind speed and direction vary with height due to the combined effects of surface friction, the Coriolis force, and the pressure gradient force. The variation of wind with height is described by the Ekman spiral, which is an idealized model of the wind profile in a boundary layer with constant eddy viscosity. According to the Ekman model, the wind at the surface flows at an angle to the geostrophic wind, crossing the isobars toward lower pressure, and with increasing height, the wind speed increases and the direction veers, which is to say it turns clockwise in the northern hemisphere until at the top of the boundary layer, the wind is approximately geostrophic. The angle between the surface wind and the geostrophic wind in the Ekman model is 45 degrees. Although in practice the observed angle is typically somewhat less than this due to the effects of atmospheric stability and the non-constant nature of the eddy viscosity. Wind tunnels, which are enclosed facilities in which a controlled flow of air is generated for the purpose of testing models and structures, represent an important complement to field measurements of wind. Wind tunnels are used extensively in the aerospace industry for testing the aerodynamic properties of aircraft, automobiles, and other vehicles. but they are also used in the fields of civil engineering and architecture for studying the effects of wind on buildings and other structures, and in atmospheric science for studying the physics of atmospheric boundary layer flow over various types of terrain. Boundary layer wind tunnels, which are specifically designed to simulate the properties of the atmospheric boundary layer, are used to study the wind loading on buildings, the dispersion of pollutants, the comfort of pedestrians in urban environments, and various other wind-related phenomena. A boundary layer wind tunnel typically has a long working section, on the order of 15 to 30 meters, in which the turbulent boundary layer is allowed to develop naturally over a rough floor, and the models to be tested are placed at the downwind end of the working section where the boundary layer has reached a fully developed state. The scale of the models is typically between 1 to 100 and 1 to 500, and the wind speeds in the tunnel are typically in the range of 5 to 30 meters per second. The study of wind and its measurement continues to evolve in the 21st century, driven by advances in sensor technology, data processing, and computational modeling. Numerical weather prediction models, which simulate the behavior of the atmosphere using systems of partial differential equations solved on three-dimensional grids, provide wind forecasts at resolutions ranging from about 1 kilometer for regional models to about 10 to 25 kilometers for global models. The accuracy of these forecasts has improved steadily over the past several decades, and modern numerical weather prediction models can provide useful wind forecasts out to a range of about 7 to 10 days for synoptic scale wind patterns. Although the predictability of smaller scale wind features, such as those associated with individual thunderstorms and tornadoes, remains limited to much shorter time horizons. Remote sensing technologies continue to advance, with new satellite missions and ground-based instruments providing ever more detailed and comprehensive observations of the wind field over the Earth. The European Space Agency's ELA satellite, launched in August 2018, carried a Doppler wind LiDAR instrument that provided the first direct measurements of wind profiles from space, and the data from this mission have been shown to have a positive impact on the accuracy of numerical weather prediction models. Future satellite missions are expected to provide even more capable wind measurement instruments, further improving the global observation of winds and contributing to advances in weather forecasting, climate monitoring, and our understanding of atmospheric dynamics. The classification and measurement of wind speed, which has been the subject of this extended and deliberately unhurried discussion, is a topic that spans centuries of scientific endeavor and encompasses a remarkable diversity of instruments, scales, and techniques. From the simple wind vanes and subjective observations of antiquity to the sophisticated radar, LiDAR, and satellite systems of the present day, the human desire to observe, measure, and classify the wind has been a constant thread running through the history of meteorology and atmospheric science. The Beaufort scale, with its elegant simplicity and enduring practicality, stands as perhaps the most successful single contribution to this effort, but it is by no means the only one. and the various specialized scales and advanced measurement techniques that have been developed over the past century and a half have greatly expanded our ability to characterize and understand this most fundamental of atmospheric phenomena. The wind, which is nothing more or less than the movement of air from one place to another in response to the uneven distribution of atmospheric pressure, is a phenomenon that affects virtually every aspect of human existence, from the weather we experience on a daily basis to the design of the buildings we inhabit, the routes traveled by ships and aircraft, the generation of electrical power, and the dispersal of pollutants in the atmosphere. The measurement and classification of wind speed is therefore not merely an academic exercise, but a practical necessity with wide-ranging implications for human safety, economic activity, and environmental quality. It is hoped that this prolonged examination of the subject has been of some informational value, and if it has also been of some soporific value, then it has served its intended purpose admirably. The atmosphere, which weighs approximately 5.15 times 10 to the 18th kilograms in total, and exerts a mean surface pressure of 1,013.25 hectopascals at sea level, will continue to circulate in response to differential solar heating for as long as the sun continues to shine, which is expected to be for approximately another 5 billion years. During that time, the winds will blow, the pressure gradients will form and dissipate, the Coriolis effect will deflect the air parcels on their meandering paths, and the anemometers and radars and satellites will continue to measure and record and classify, adding ever more data points to the vast and growing archive of wind observations that humanity has been accumulating since Francis Beaufort first put pen to paper in his cabin aboard the Woolwich in 1806. And so the measurement and classification of wind speed scales continues, as it has always continued, one observation at a time, one knot at a time, one Beaufort force at a time, in the slow and steady and thoroughly unremarkable manner that characterizes all of the best and most enduring scientific endeavors.